And our next presenter is Yoni Xiong. She studies radiation effects and reliability at Vanderbilt University. And she did her practicum at Sandia National Laboratories in New Mexico in 2023. Please take it away.
All right. Hi, everyone. Thanks for the introduction, Samantha. So like she said, I did my practicum at Sandia National Labs in 2023. And this is part of that work that it took off from there. And today I'll be talking about single particle displacement damage effects in advanced semiconductor technology nodes. These are the type of technology nodes that are used widely in cutting-edge commercial devices and will become soon relevant to defense applications as well, especially with that modernization of the stockpile like mentioned before. Displacement damage from radiation can cause permanent operational failures in electronic circuits. So my work is focused on evaluating displacement damage effects in SRAM circuits at the 14 and 5 nanometer bulk FinFET nodes. So first, to set the stage, I want to go over what are radiation effects and why they're interesting to study. Radiation effects refers to how radiation particles like protons, electrons, and heavy ions will affect certain things, and in my case, how they affect electronic circuits and systems. So radiation is going to originate from many different sources. There are solar particles coming from our sun due to events like solar flares and coronal mass ejections. And there are also a variety of high energy particles coming from deep in outer space from other stars or supernova events. Every environment has different amounts and types of radiation. So for instance, around Earth, where satellites are orbiting, there is a trapped belt of electrons and protons due to the Earth's magnetic field actually trapping them in that area. So you can see how satellites, which are very high reliability systems, would need to be aware of the possible effects. On Earth, the terrestrial environment also has a variety of particles, mainly neutrons, and this is a concern for systems like planes, cars, data centers, as well as systems associated with stockpiled stewardship. I like to think of this area of nuclear science research as having different levels of abstraction. A lot of the fellows here, like Garrett and Benjamin before me, focus on the particle and material levels of abstraction for nuclear physics and material science research. My research lies more on the circuit level, where I take a look at how those fundamental particle interactions actually manifest as observable changes to circuit level parameters. And then understanding what happens at the circuit level allows us to inform changes and decisions that could be made at the system level. So the circuit that I use in my research is an SRAM circuit. This is a static random access memory cell, a very standard component to all electronic systems for implementing on-chip memory. So this circuit stores a binary 0 or 1 value, and each one of these is called a bit cell, and many of them together form an SRAM memory array. And the memory array, you can then arrange all these bits into different like words, bytes, and assign them addresses for computing. In each bit cell, there are 6 transistors. Each of these transistors work together in order to allow this bit cell to function properly. Whenever it does function properly, you would expect the bit cell to correctly store data that you write to it. So if I write a 0, I should read a 0 later on. But if one of these transistors fail to function properly, then this whole bit cell can fail and become stuck at a certain value. For instance, if this transistor stops failing, then it can only store a 0 value no matter how many times you attempt to write in a 1 value. So if you have an instance where data could be wrong at a certain place in your memory, this can have very unintended consequences at the system level. For instance, for a very critical application, like perhaps a defense application, if this memory bit corresponds to part of a command or navigation information, then you can see how this could result in bad things happening. So like I said, radiation can cause these types of permanent failures, and one of those mechanisms is called displacement damage. Here I have this lattice of blue spheres representing the silicon atoms that make up the semiconductor devices and materials forming our circuits and systems. And let's say this red ball is an incoming radiation particle. it could physically displace one of the silicon atoms from its original position in the lattice, and then that displaced silicon atom could then displace other silicon atoms, forming a bit of a cascading effect and creating ultimately a fairly large defect in the semiconductor material. These defect sizes have been measured to be as large as 10 nanometers in size for silicon and other studies. And for the latest advanced technology nodes, we have transistors, thin field effect transistors at the sizes of 14 nanometers, 5 nanometers, and even 3 nanometers in size. And that dimension corresponds to approximately how long that part is on the FinFET transistor. And with every generation, we've been attempting to shrink these transistor sizes every few years so that we can have advances in transistor processes and therefore computing and processing power. And the industry only plans to keep making these transistors smaller and smaller. So this is where you can see an issue arising. These damage defects are now comparable in size to our transistor sizes. So it's important to understand whether there's a potential reliability concern for these permanent failures on the system level. And my work is focused on evaluating these displacement damage effects at these advanced semiconductor technology nodes and to see to what extent there could be an issue. So to evaluate these effects, I used custom test circuits, and I took a look at, again, the 14 and the 5 nanometer technology nodes. The 5 nanometer work I did majority during my practicum at San Diego National Labs, and that's already been published at the IEEE Transaction Nuclear Science. So for this talk, I'll be focusing on the more recent 14 nanometer work that is in progress. So for the 14 nanometer node, I evaluated 2 different circuits, a high density SRAM and a high performance SRAM. For the high density SRAM, each one of these 6 transistors only has 1 fin in the FinFET structure, meaning that we could have the smallest area possible for this SRAM cell on the integrated circuit. And the high performance SRAM, on the other hand, these NMOS transistors here have a second fin, allowing for this cell to have faster reading and writing speeds. And this does come at the cost, though, of higher area. And higher area also does mean higher physical cost for these type of chips. Designers use both of these designs throughout their applications, and they just have to weigh the pros and cons of whether you would like higher density or higher performance. So to do the study of evaluating, I irradiated these test ICs using oxygen ions at San Diego National Labs with their ion beam lab facility. This is the Casper 3 end station, and this is what the IC would look like with my test setup and board. Throughout the irradiation process, I would monitor the functionality of each of the bits in my SRAM by reading and writing known memory patterns. And then I would record whenever a bit failed, would be stuck at 0 or stuck at 1. So this is what the results would look like. So I measured the number of failed SRAM bits as a function of total oxygen ion fluence for both the high density and high performance SRAMs. As you can see, as we irradiated the device at higher fluences, more SRAM bits would fail. And the high performance SRAM had less failed bits than the high density SRAM. And this is likely due to that second fin in the SRAM design. Since each one of these transistors needs to work properly, having that extra fin on those NMOS transistors means that if this fin gets damaged and experiences some degradation, the other fin can help out and this transistor still functions. Whereas for the one fin design, each fin is by themselves, fending for themselves. If they experience damage, then that whole transistor is out and then the whole bit cell is out. From those results, we could also see that we did observe single particle induced stuck bits. This means that it was due to a single particle that the whole SRAM bit cell ultimately failed. And this is an important observation because the radiation environment is filled with particles, and if any one particle could cause your bits or your memories to fail, then that's very important. We were able to distinguish single particle effects by looking at the rate of increase in the number of failed bits as a function of fluence. Since single particle effects are stochastic probabilistic effects, they will increase linearly with respect to fluence, like this region here for the high density SRAM. And the cumulative particle effects require the accumulation of multiple particle events and therefore increase superlinearly with a steeper slope on these log-log plots. And this study is actually the first experimental observation of these single particle effects occurring in a modern digital circuit design. So it's very important for the industry to be aware of this possible failure mechanism. I did many other experiments to confirm that the failure mechanism is in fact displacement damage and not other radiation effects. I used different energies of heavy ions, and these different energies allowed for me to maximize displacement damage versus other ionizing effects. I measured the changes in ring oscillator frequencies and compared the results from different energy sources like 10 kV X-rays and heavy ions to differentiate total ionized dose effects and displacement damage effects. And I also took a look to see if those failed bits could be recoverable with high temperature annealings after the irradiations. And all of these studies did just ultimately point to displacement damage being the failure mechanism. And then finally, I did simulations and modeling to understand what type of defect distribution is needed to occur within the SRAM cell to manifest as a stuck bit. I did defect simulations for oxygen ions and silicon to measure and have a data set of the vacancy production in that material. And I used that information along with SRAM layout and fin volume to conduct a Monte Carlo simulation campaign where I was able to develop a generalized model defining SRAM bit cell failure as occurring once a certain defect distribution was reached within the SRAM design. And then I compared that generalized model with the experimental data to see good agreement, which would indicate to us that there is a direct correlation between the defect formation in the material with circuit level failure. So just to conclude, displacement damage is predicted to become problematic at these highly scaled technology nodes due to the defect sizes now being comparable to transistor sizes. Displacement damage was investigated at the 14 and 5 nanometer node S technology nodes using SRAM circuits and high fluence heavy ion experiments. And I developed a model to demonstrate the correlation between displacement damage production and stuck bits to compare with the experimental observations of other stuck bits in both designs. Displacement damage-induced failures may become increasingly probable with continued scaling advancements, and the industry may need to address these types of failures in critical systems and for this audience, particularly for those used in the stockpile. Thank you, and I'd be happy to take any questions.